Principal component analysis. It is a dimension reduction method. All right, that's basically what it is about. What do I mean by dimension reduction? Let's suppose you have a data set and data set with n records and p variables, right? And p, let's suppose, is large. So what are we going to do is that sometimes it is very difficult to understand what's going on in the data with all these variables in your data set. Given that many of these variables are correlated among themselves, it might be better if we come up with a new set of variables such that these new sets of variables are not correlated among themselves. Okay, so what is the idea is that instead of working with 100 variables, you come up with a case where you are going to work with a fewer set of variables. Let's suppose 3 variables. So what is happening here is that these 100 variables turn up to be a new set of variables. They are transformed into a new set of variables. And these new sets of variables will look at a fewer set of variables. Now, what is this transformation and what are all these about? That's what I'm going to discuss in a moment. But just understand the principle. The principle is that you are reducing the dimension of the data in such a way that instead of working with 100 variables, you're now going to work with a new set of latent variables, all right? A new set of latent variables uh, that will be more manageable and that will help you in interpreting what's going on in the data. And what does these new sets of variable represent? We'll get to that in a moment. So why do we carry out principal component analysis? One of the reasons is to apply it in supervised learning methods. So what do I mean by applying in supervised learning method? Let's suppose you have these different set of variables on which you have applied the principal component analysis, and you want to predict a certain target variable y. Now, using these variables to predict the target variable y is not always a good idea for one simple reason that it will result in overfitting, as we all know. Now, but which means that normally your error in the training set will be very small, but the error in the testing set would be very large. So it's not a very good idea to take all these variables to fit y. So then what happens is that this is the idea of principal component, is that you derive new variables, like let's suppose a fewer set of new variables that will be used to predict the y. That's the idea. Instead of working with all the 100, you're now going to work with 3 that will predict the y. So the 3 will capture sufficient information that will allow you to predict the y. That's the principle behind the principal component analysis. So that's one of the reasons. The other reason, of course, is to visualize the data. Is to visualize the data through the means of, for example, a biplot. I'll get to that later on, but just to get you in the picture is that we can also use a PCA as a visualization aid. The idea is to see, for example, what are those variables that are associated with each other. All right. So this is one of the reason why we want to do PCA. It is important to note that the PCA is an unsupervised learning method. An unsupervised learning method means it does not have a target. Please do not get confused with what I mentioned here. All right. We can use PCA. A Normally we can use PCA to derive variables to be used in supervised learning, but PCA itself is not a supervised learning method. All right, it is unsupervised because if you look at these sets of variables, you don't have any target among them. There is no output variables here. There is no target. This is why it is an unsupervised learning method. But when you get the new set of variables, you may wish now to use it in a supervised learning. That is, you are going to predict y using them. But Originally, PCA does not have a target. So, in other words, it is an unsupervised learning method. So these the ideas I just said to you is that you want to reduce the dimension of the data. You might have p variables like 100 variables, but in the end you are deriving only, let's suppose, two variables from these 100 variables, and these two variables are sufficient to explain these 100 variables, right? To explain what's going on in the data from these 100 variables. So, in other words, you are moving from a high dimension to a low dimension representation of your data. Okay. Now, here we are referring to two, but it depends. You might wish to have more than two latent variables. You might have three, you might have four, you might have five. It all depends on the data set that you have and the context of what you are looking for. We'll get to the idea of how to decide on the number of components for our analysis later on. So, what is a PCA about? A PCA basically, as I just told you, is a dimension reduction method. But the principle in applying the PCA is that we want to kind of find a linear combination, all right, a linear combination of our feature that has the largest variance. So basically here, if you look at this here, you have a linear combination of your random variable that explain your the largest variance. What does it mean? It means that let's suppose you have a data set. Let me just go to the next slide. Let's suppose you have a data set. To understand this concept, let's take it like that. Let's suppose you have 4 points going on in your data like this, okay? Now, if you imagine these 4 points here, just imagine you have an hyperplane within that point. An hyperplane means you have a line. There are two variables. We are assuming that there are only two variables, all right? V1, and we are assuming in the data set that there are only two variables, V1 and V2. Let's imagine you have an hyperplane within that data. The hyperplane, the idea is we call it x2 and x1 rather than v1, v2. So the hyperplane is the one that will come up because this can be represented in the form of an hyperplane, all right? Here, this hyperplane means a line basically. There are different dimensions of hyperplane. There is one of it is a line. The lowest dimension can be represented as a line. And the idea is that this line should give us when we are combining all these random variables together, when we are combining the feature space together through the linear combination here, we want to have this new variable, this transform variable, to have the largest variance as possible. And how can we get the largest variance? Just imagine these 4 points. And the line that is going to go through the data should be the line that explains the largest variance. Let's imagine for a moment you have a line that goes in the data like this. Okay. If you look at the perpendicular distance between this line and the points, all right, if you look at the perpendicular distance between this line and the points, that's basically what you have here. So if you were to rewrite this on the, and if you want to rewrite this line on an horizontal format, this is a line. Just imagine those 4 points, how they are going to be scattered on this line. You will have here, this is a point here, this is one of it, this is another one, this is another one, and this is another one. So we are like equidistant if we want to have a look at it like that, kind of equidistant. So you have a point here, a line, and then you've got something like this, you get something like that, and you get something like this. Okay, if you represent this. Now imagine a little bit a different kind of line that goes on the data like this now. Okay, a different kind of line that goes on the data like this. And you look again at the perpendicular distance between these point and the line. You drop a perpendicular line between these lines and the points. All right, just imagine that for a moment. Here we go. Here we go. And here we go. So if you look at the points now on the hyperplane, all right, the point on the line. Okay, look at that. Try to represent it on this, on the horizontal format. You will have 2 points that are very close to each other, and they are very separate as well. So you have 1 point here like this, and you have 1 point like that. This is what you get in terms of representation. Now imagine all the different possible lines that can go through that data. What we want is that we want the line that will explain the largest variance possible. That is, your new variable z would explain the largest possible variance. Like here, if you look at these two lines, which one will give you the largest possible variance? Logically, this is the line that gives you the largest possible variance, because if you look at the center here, you will see that those points are more scattered than those points are more scattered than these one. If you look at the center here, the points are not that much scattered as compared to the first one. So in other words, this, if you want to compare between these two lines, it is this full line compared to the broken line. The full line is explaining the highest variance. So what is the principle here? We want that linear combination that will explain the largest variance. And of course, the linear combination will have some weights attached to it. Like for our example here, you can just imagine it in terms of two variables. So you will have a certain weight that will define a direction, a vector, all right, where the line is. That is this theta 1, 1 and theta 2, 1 would be defining the vector that would be the defining the it's going to be a vector theta, sorry, not theta but phi 1, 1 and phi 2, 1. Phi 2, 1 would basically define the direction of the line that explain the maximum variance. So this theta 1, 1 and sorry, not theta, but phi 1, 1 and phi 2, 1 will be the vector that define the hyperplane, or define the line that will be explaining the maximum variance. All right, so you cannot use any kind of phi 1, 1 and phi 2, 1. You will have a specific value for which it will maximize the variance. Like for example, if you use a phi 1, 1 and a phi 2, 2, which gives you a certain vector in a direction like this will not maximize the variance. But if you use a phi 1, 1 and a phi 2, 1 that gives you a direction like that, you may think that this is maximizing your variance. So what is this value and what is this value? We will get to that later on through the concept of eigenvectors, all right, which we'll discuss afterward. But another way of looking at this, when we are referring to the largest variance, another way of looking at it is to find a line that is closest to the data, right? Like if you look at the broken line, it is not closer to the data. Why? Because if you look at the distance between this point and the broken line, it's very far. So it cannot be considered as the one that gives you the largest distance. However, this one, the closest distance, excuse me, this one is giving you the line that is closer to the data, because in the end you will have the smallest sum of residual squared error, rather. You will have the smallest sum of squared error if you look at this line. But this line will not necessarily give you the smallest sum of squared error. It is only this line that will give you the smallest sum of squared error. So what did we come up with here? we've come up with a new variable z1 that is defined as a linear combination of your features that has the largest variance that I explained to you here. So, in other words, if you want to look at z1, you can look at it as a new axis going on through your data. Originally, you had your x1 and x2 like that. But now imagine that this new z1 that you are referring to here, this z1, imagine that this Z1 line now becomes your new axis. So just transpose that and make it horizontal like this one. So it's like reorganizing your data. It's like transforming your data into a new set. Your points that were originally here will be moved on a new set of axes where you have Z1 here, and those points would be located somehow like this on the new axis. Okay, so remember that you are moving from X to a new set of variables now. So how did you get this new set of variables at one? Through a linear combination of your feature space. Now, this is not sufficient. You have one that is explaining the largest variance, but what is the next one that explains the largest variance? The next one should be another vector or another component. You have the first principal component that has been obtained. You can get a second principal component because if you have two variables, you can get two principal components. If you have three variables, you can get three. If you have four, you can get four, and so on. But like in this context, you have two variables that are represented, which means that you can have two principal components. The second principal component is basically a bit the same idea like what we explained. We want the largest variance, but the only thing is that we add a certain additional condition to this one. Remember that earlier I told you that when you have a set of variables like these variables, they are correlated among themselves, all right? So what is happening is that you will have a new set of variables that are meant to be uncorrelated among themselves. Because the x are correlated, you don't want the z to be correlated because you want all the correlated variables to be captured in one particular principal component and another set of correlated variables to be captured in another set of principal component, which means that these two are meant to be uncorrelated. And the only way to ensure that they are uncorrelated is if you have the first principal component, if you have been able to find the first principal component, it's very simple, is that now you can imagine an orthogonal vector. That is a vector that or a direction of a new line that is now orthogonal, that is perpendicular to the correct one. If you found the Z1, finding Z2 is relatively easy, is that you can imagine a new axis where your which is perpendicular to the Z1. All right, a new axis which is perpendicular to the Z1. And this new axis will now explain the next amount, the next amount of proportion of variance in the data. And this continues if you have more variables, right? If you have more variables, you can have more, obviously, more principal components. But to simplify explanation, we are referring only to two principal components here. So obviously, if the Z1 has these vector of weights that has got a specific name that I'm going to show you in a moment, which we refer to as loadings, all right? What are loadings? We'll get to that afterward. So if Z1 has got this, Z2 should have a different direction, a new theta, a new set of theta, phi, excuse me, a new set of phi that is different from this one, that would be orthogonal to this one. Okay, so just to sum up, what we have done here is that we have just applied a transformation to our variables x1, x2, and this transformation that we are applying, we want it to be in such a way that it captures the largest amount of variance. In other words, this Z1 should be capturing the highest amount of variance. Now, how is this going to be done? As I told you, we will get to that later on because it will refer to a concept of eigenvector. Okay, it refers to a concept of eigenvector that we are going to discuss afterward. Uh, but for the time being, I'm just referring to the principle. Now, there is one thing that you need to understand is that if you want Z1 to have the largest variance, all right, to capture the largest variance, one of the things that you might say, okay, because very often what we are trying to do here is to estimate these phi values, all right? We want to estimate these phi values. And how do we get these phi values, these phi, that is these, as I was saying to you earlier, that we refer to as loadings? How do we get these loadings? In such a way that when we are increasing, we want to increase the variance here, we don't arbitrarily increase these. So there is a problem because when we say we want to have a linear combination of features that has the largest variance, you might be tempted to say, okay, let's arbitrarily inflate these values. And if we arbitrarily inflate these values, what would happen is that obviously the variation for Z1 will also be inflated. This is why we have to be careful. We have to put a certain constraint that you see there. And this constraint acts as a normalization. What is the idea behind is that you don't want the normalization will normally we do not want to make use of large values of phi. We do not want to make use of large values of phi that will make the variance of Z1 large. That is, we don't want to arbitrarily increase or inflate these phi up to a point that will increase the Z. So we want to impose a certain restriction on them. We want that their sum of squared equal to 1. This will prevent us from inflating these phi to a high degree that will also inflate this. So to avoid this arbitrary inflation of your variance, this is why we impose that condition here. As I said to you, phi 1, 1, phi 1, phi 2, 1, and so on are referred to as the loadings. In the example that we just discussed here, we had phi 1, 1 and we had phi 2, 1, like because we were referring only to two variables. But in a data set, you don't have two variables, you will have so many possible variables, phi up to phi p1. So the vector, all right, the transpose of this, if you want to look at this, can be represented as phi 1. Phi 1 means it is a factor loadings with regards to the first principal component. Remember what a principal component is. It's a linear combination of your random variable. So these phi values, phi 1, is basically phi 1 is representing your first factor loadings, all right? And then you have to understand that you can get a phi 2 as well. Phi 2 would be equal to what? Phi 2 would represent phi uh, phi 1 2, all right? Phi 2 2, phi 3 2 up to phi p 2. All right. Now, just imagine how many possible vector loadings you might have. If you have p variables, you will have p vector loadings you may wish to have. All right, p vector loadings. So this is a little bit what these are about. Now, these loadings are kind of talking about the importance that these variables have on the principal component. To make it a little bit simpler for you to understand the loadings, just imagine we get back to this one and we are referring to a first principal component. We will also have a second principal component and so on, but let's talk about the first principal component. If the phi 1 1, phi, let's suppose 3 1, phi 5 1, and phi 6 1 have high loadings on your first principal component. What do I mean by have high loadings? It means that these values are higher than the others, bearing in mind that if you take the sum of the square of all the possible phi's, you should get 1. But think about if 511, 531, 551, 61, and some others are having high loadings. They are compared to other uh, overloadings. All right. If we are having high loadings, that would mean what? It would mean that variable 1, variable 3, variable 5, variable 6 are strongly correlated among themselves. That's what it would represent. So the higher the loadings, the higher the probability that these variables are correlated among themselves. So that is the principle behind the principal component analysis. You want to get those variables that are highly correlated among themselves to be represented in your first principal component. And this process will continue like the Z for Z2, that is the second principal component. You will have the same idea. These loadings that are high on Z2 would be those variables for which they are strongly correlated on Z2. So in the end, based on that, you can also get an interpretation for what Z1 represent and what Z2 represent. We will come to that again through an example afterward. Okay, so here, as I said to you, we can mathematically represent everything that we have been discussing through what you see in this slide. To understand that, it is important that you understand that we are going to refer to a data matrix. That is, you remember the x1, x2 up to xp that we were discussing and the 1, 2 up to n. Now, we are referring to this data matrix as a centered data matrix. Centered data matrix means that we are demeaning, that is, we are removing the mean from x1, we are removing the mean from x2, and so on. That is, we are not referring to the original variables, but we are dealing with a centered data, all right? This is very important that we are dealing with a centered data. That is, you will have the mean of all x1 to be equal to 0, the mean of x2 would be equal to 0, the new x1, all right, and the new x2 would be, their mean would be equal to 0, because originally they are not going to be equal to 0. If you're talking about sales, you are talking about price, you're talking about whatever, their mean would not be equal to 0. So what we do is that to understand the principle of principal component analysis, we need to assume that the data matrix that we are dealing with is a centered one. Okay, that's very important because all the mathematical explanation is based on the fact that they are centered. Now, centered means the mean has been subtracted from the data. So remember that we told something is that we want to have the linear combination. The first principal component is linear combination that will maximize the variance. All right. Now, when we talk about maximizing the variance from a now just let's have a look at the variance first of all. We all know that the variance of a variable is going to be defined as 1 upon n sum of x squared minus x bar to the squared. That's what we already know. Okay, but in a data, if your data x is already centered, this x bar would be equal to 0. So which means that in the end, you are referring just to the sum of x squared, 1 upon n sum of x squared. But here, you are not going to talk about only sum of x squared, you have also to talk about the loadings. So this is why you see this formula here. What we are trying to do is that we are representing that as a linear programming problem, but the way it is going to be solved is going to be discussed afterward. But for the time being, the objective is that you want to maximize the variance. And maximizing the variance is obtained by the squaring of these linear combinations of the random variables divided by n. Of course, subject to a constraint. Now, this can be simplified a little bit further because we have said that Z1 is a linear combination of those. So if this is the case, we can simplify it a little bit further into this formula here. So we want to maximize 1 upon n sum of z I squared, right? This is basically talking about the variance of your zi squared. Bear in mind that your Zi1 here is the first principal component. The variable Zi1 represent your first principal component, and the value that you will get from them, the small value Zi1 that you get from your first principal component, would basically have a mean of 0 as well. Why they will have a mean of 0? Because xij themselves have a mean of 0. So obviously xzi would also have a mean of 0. This can be proven mathematically, all right? If you just look at that. You can continue it afterward. I'm just giving you an idea. J is equal to 1 up to, let's suppose you have zi. Zi is equal to the sum from j is equal to 1 up to p of phi j 1 xij. All right. So this is what I'm referring to. So z I1 is equal to, so the j would change with respect to the variable, but the 1 stays the same as you see, and you are referring to xi j. J will again change and I will also vary. Now, if zi is equal to that, you need to understand that also that z bar is equal to what? So here we are referring to z bar is going to be equal to what? 1 upon n, the sum from I is equal to 1 up to n, from j equal to 1 up to p of phi j1 xij. And this same thing can be extended further by 1 upon n. You take the constant out, and you can also interchange the summations. By interchanging the summation, you will see that later on you can prove that z bar is equal to 0. You continue this process because you will come up to a situation where you would have the sum of xij, right? And the sum of xij is equal to 0 from what we already know. So you continue this process, you will see that z bar turns out to be 0 because this is 0. Okay, you carry on the process later on. So we can just have a look at the interpretation of the first principal component. As I told you, it's going to be the vector that is maximizing the variance. Another way of looking at it, it's going to be the vector for which you have the points that are closest to this line. Okay, and obviously the first principal component here is the green line that you see here, the first principal component. And this first principal component is going to be represented by a vector, a loading vector. Okay, like in this context here, you have only two variables that are represented, so you will have like only these two loading vectors. These two loading vectors give us a direction of our first principal component. The direction should be like that, should be like this, or should be like that. This is what it gives us. Okay, the loadings. And later on you will understand how we find out these loadings. That is, how do we really find out what is the value of phi 11 that correspond to this, and phi 21 that correspond to this line. So this is what we are going to discuss through eigenvalues and eigenvectors later on. So remember that this first principal component can be viewed as new axis. Just imagine you rotate that, and you rotate it in such a way that it looks like this now. Okay, but it looks like this. So this whole data set will be transformed in that new set of values that will be rotated in such a way that the new axis does not represent population anymore, but represent Z1, and this one represent the advertising is no more advertising, but a new component Z2. Okay, so that's the principle here. Now you have to understand that even if you have more variables, you can also represent it on a two-dimensional plane. That's also possible. Okay, even if you have more variables, 3, 4, 5 variables, you can still represent it on a two-dimensional plane. That is, you can represent it through the first principal component and the second principal component. The first one will always give you the maximum variance. Then come another one that gives you the next maximum, and it goes on like that. Okay. So I leave the detail for the second component, which is basically the same idea like what you did here. We want to still maximize the variance, so the principle is going to be the same, subject to the same constraint that we discussed earlier, why we have this constraint, but the second principal component has an additional constraint that has to be set. And this additional constraint relates to the fact that theta that is phi 2 is orthogonal to phi 1. When we are referring to phi 2 and phi 1, just remember what phi 1 represent, yeah? So phi 1 represented what? Phi 1 represented phi 1 1, phi 2 1 up to phi p1. What does phi 2 represent? Phi 2 represent phi 2 represent phi 1 2, phi 2 2 up to phi p2. That is going to be our phi 2. So what we are trying to say is that if you have remember that a vector gives you a direction where your hyperplane is supposed to be. So if this is giving you a certain direction like that, if you have two, let's suppose you have only two there, all right, the other two should give you a different direction, which is like this, as I explained to you earlier. So when, in other words, these set of vectors, they are meant to be orthogonal. That is, they have to be perpendicular. If one is giving you a direction that goes in this side, the other one should give you a perpendicular this direction. That is the direction that goes on the other side. And this is an additional constraint that you need to add to your maximization problem. Subject to this and subject to the idea that the new loadings are also orthogonal with the first one. But you would note that we will get to avoid all these details of we will get to avoid the details related to the maximization of the second principal component, but just understand that there is an additional constraint there. Okay, but how do we relate to these phi 1 1, phi 2 1 up to phi p1? How do we get these values? All right. How do we get the values for phi 1 2, phi 2 2 up to phi p2? How do we get these second vector loadings? That is phi 2. How do we get phi 1? How do we get all these? All right, transpose. How do we get all these? This is what we discuss here through the principal component decomposition. We will talk about how we get these phi 1 and phi 2, that is these vectors. These vectors are going to, the loadings are going to represent what we refer to as eigenvectors, right? So, and to understand the principle behind the principal component analysis, when you are maximizing, remember the principle is to maximize the variance with respect to phi 1, phi up to phi p. So what are we trying to do here? We want to have a value of phi 1 up to phi p, one that maximizes this thing, right? And how do we do that? This is where I'm discussing now. To understand that, let's take a context where you have a n by p centered matrix. I repeat, centered data matrix. Just as I told you earlier, x1 up to xp, up 1 up to n, but these x variables, they are centered. These their means have been subtracted. In other words, the new data matrix x that we are referring to has a mean of 0 and everywhere for each column. So there's a small typo here. This phi should be written a little, capital phi a little bit differently. So this should be written as phi like that. Excuse me. And for this one as well, there's a small typo that we are going to correct here. And this should be written as this one. Here we go. Same thing applies for this one. Here we go. But I just need bold to represent that it is a matrix. A matrix. Here we go. So this is done. Just check that for a moment. Everything seems good. So yes, let's get back to what we were referring to here. We are going to define a phi as a p by p matrix. All right. Now, when I refer to phi as a p by p matrix, what do I mean by that? Just remember something. Is that earlier I told you um, if you have two variables in your feature space, x1 and x2, you are expected to have two eigenvectors. You will have two, not eigenvectors, but you will have two factor loadings because x1 and x2 can be transformed into z1 and z2. Now, if they are transformed into z1 and z2, that would mean that you would have a factor, a direction that is going to be given for z1 and a direction that is obtained for z2, all right, in the data originally. So if you have a direction for Z1 and a direction for Z2, they are orthogonal. That would mean what? That would mean that you would have a set of two um, a set of two vectors. All right. So if you have a 2 by 2 matrix, what's going to happen is that you would have a vector of 2 by 2 a 2 by 2 matrix of factor loadings, all right, those phi 1 and phi 2 that we were referring to earlier. So you would have a 2 by 2 factor loadings matrix. You can think about it like that if you want to make it a little bit easier. You can think about it like phi 1 1, phi 2 1, phi phi 1 2 and phi 2 2. All right, so in other words, you have the first vector loading phi 1 for this one and the second vector loading for the second principal component phi 2 here. So that's a little bit the idea behind. All right, but of course if you have p variables there will be more than that logically, and remember that they are representing loadings. All right, and these loadings are what we would refer to as eigenvectors. All right, now the idea of eigenvalues and eigenvectors are omitted in this lecture. All right, this is something that has been discussed in year one module where we referred to the uh, concept of eigenvalues and eigenvectors. We are just explaining what they are referring to. Now, for the reader who needs to recap a little bit on what eigenvectors and eigenvalues are, just understand that at the end of the slides, I have given you a small section where you can go through eigenvalues and eigenvectors on your own. You may wish to learn about eigenvalues and eigenvectors by the end of the section where you will see, let me just get to there. Here we go. The end of the slides will discuss a little bit about how you find eigenvalues and how you find eigenvectors, if you want to really know what they look like. But for us, what is more interested is not how to compute eigenvalues and how to compute eigenvectors, though this is given at the end of the slide, but rather to understand what eigenvalues represent and what eigenvectors represent in our context. That is what is essential for us to understand for the time being. Okay, so as I told you, the eigenvectors, they are basically referring to the direction, all right, of your, it's a vector that will give us the direction of our first principal component, and it gives us the direction of our second principal component. So the vector here is giving us the direction. And now the loadings, the fact the loadings is what is giving us the direction, but then you will also have something that we will refer to as eigenvalues. For each eigenvector is associated with an eigenvalue, all right? This vector, it has not been obtained just like that. It has been obtained associated with a certain eigenvalue. Now, the eigenvalue, let's suppose lambda 1 and a certain eigenvalue lambda 2. And this eigenvalue also has an interpretation to it. All right, the eigenvalue lambda 1 would represent the variance for the first principal component, and the lambda 2 would represent the variation for the second principal component. And it goes on like that if you have more variables. Each of these lambda would represent the variation in the principal components. Just remember that, okay? Each of these lambdas represent, that is the lambdas represent the eigenvalues, they represent the variation. So normally what is going to happen is that when you are going to have, let's suppose, p variables, which is, let's suppose, 3 variables, you would have 3 eigenvalues, and these 3 eigenvalues represent the variation in the date explained by z1, z2, and z3. Obviously, z1 will always be the one that has the highest proportion. But then what happens is that the forthcoming one, you will need to look which one is the highest. If lambda 3 is giving you the highest variance, you would order it here first, and then you would order lambda 2 afterward. And then when you are representing your matrix, you would always represent the matrix in the form of the one that has the decreasing order of variance. This is what we do in the next slide here through S, all right? Through S, this is what we do. But let's get back to this one. I don't want to move too fast. So here you have the phi, which is the eigenvectors of what? We've been referring to eigenvectors of a matrix. What matrix? Not the matrix X, but the matrix X transpose X. It's like the variance covariance matrix. But just for your information, we are not talking about the divide by n here. We are referring to just the sum of x squared here. So what is happening here is that the phi is the phi, which is our loading, vector loadings. They are basically eigenvectors that are obtained for a matrix, X transpose X. X transpose X is just like finding the variance covariance matrix. So you will have a variance here and you will have a covariance that will be obtained here. The covariance might be negative, but the variance will always be positive, okay? The variance of a first variable will be here, the variance of a second variable will be here, and the covariance would be found off diagonal. But on the diagonal, you will have a variance. So X transpose X transpose times X represent the scaled covariance of the data, okay? As I told you, the covariance matrix. Now, the principal component, what is it about? Just remember the formula as I explained to you earlier. The principal component, if you look at it, is a linear combination of your random variable with the loadings. Okay, so if we are taking the loadings to be represented by phi, so our random variable x, if you multiply the matrix, now it's just that we are representing in matrix notation. Okay, now, the matrix X multiplied by the factor loadings is analogous to what you see here. Okay, you are taking the matrix X multiplied by the factor loadings. So that is a little bit what you are doing here. So Z, the principal component decomposition of Z, decomposition Z of X is defined as the matrix X multiplied by the factor loadings. So this is just analogous to what you have seen in the previous slides, like here. Okay, so but just instead of representing it as a linear algebra there, but we are representing it in terms of matrix notation. That's the only difference. So the data is now transformed into a set of p-orthogonal components. Remember that they are orthogonal because we want them, if one has explained the maximum variance, we want the other one to be uncorrelated to the previous one. The only way that they are uncorrelated is by being orthogonal. Like if you have Z1, Z2 cannot be something like this. Okay, Z2 cannot be something like that. Z2 should be something like perpendicular with Z1 so that they are uncorrelated with each other. All right, that's one of the things that we want to ensure. Now, we want the eigenvectors to be ranked by the largest eigenvalue. As I said, the eigenvectors here, they are representing the loadings, the factor loadings, and the eigenvalue is what is representing the variation, all right? They are representing the variation. Just remember that the Z will represent the component scores. The matrix Z, when you are multiplying it by X, you will get the component score because X is what? X is a N by P and phi is a P by P. So in the end, what do you get? You get something that is similar to your data matrix X. So your X has been changed into new variables. Remember that when you are applying principal component, you are basically transforming your data. So what did we do here is that we have transformed the data into a new set of values. So the next thing that we want to do is that when you have been able to transform your data into a new set of values, and these new set of values Z1, Z2, and so on, which represent the first principal component, the second principal component, and so on, would be used somehow for supervised learning, as I explained to you earlier, or it may not be used for supervised learning, but it may be used to visualize the data, right, on a smaller component. Now, as I said to you, how do we get these phi values? These phi values are obtained by obtained by the eigen vector of that matrix. All right, so to find these phi, we just need to find the eigenvector of x transpose x. So this is how we get these phi that were looking a little bit difficult at first sight. You might ask yourself, but how do I get these values? What is these values that maximizes this x, this z here? What is this value that what are these values of phi j's that maximizes the variance? The value that maximizes variance is obtained by looking at the eigenvectors. And as I told you, to understand more eigenvectors, please refer to the last section of this PowerPoint slide where this is discussed again. So when you've got your matrix Z, what we want to do is we want to consider the matrix uh, S, which is Z transpose Z. Remember that earlier we did X transpose X. That is, this is what gave us the vector of The eigenvector of x transpose x is what gave us our phi matrix. But then now, what was x transpose x? It was our scaled covariance matrix. But now, what we want to do is to get a scaled, we want to get a covariance matrix of Z transpose Z. That is, we don't want to have a look at the covariance of this one, but we want to have a look at covariance of this one. Why do we want to do this? Because when you are going to look at the Z transpose Z matrix, just imagine the covariance for X transpose X, right? You would have a set of values. Imagine you have only two variables, all right? So you would have a 2 by 2 matrix, and you will have values here, values here, values here, and values here. But when you look at the X, Z transpose X, Z, you need to understand something is that when you would look at the variance covariance matrix, you would have a certain value for the diagonal, all right? You would have a certain value for the diagonal, but for the off diagonal, you expect to have zero, you expect to have no variation, because remember that the variance covariance matrix can also be viewed as a correlation matrix, where you would have a variation here and you would have the correlation here. But the correlation in the off diagonal from a correlation matrix, if it is equal to 0, would mean that the first variable and the second variable are uncorrelated. So if they are uncorrelated, it means that the covariance is 0. So covariance of 0 means there is no correlation between the first and the second variable. So this is what we expect, is that if we do Z transpose Z, we will have the off diagonal to be 0. But what is of interest to us is the diagonal. Through the diagonals, you will know what is the proportion of variation that is explained by the first component, and through the second value here, you would know what is the proportion of variation that is explained by the second component. So this is how you will get to know what are the proportion. Normally, the first one will explain the highest proportion of variation, then will come the second, and then will come the third, and so on. So, in fact, the diagonal will give us this information about the the scale variance of each component, right? It gives us the scale variance of each component. So, what is of interest to us is the diagonal elements to explain the proportion. The higher the proportion is explained by the first few factors, when which means that you will select only the a few factors. But let's suppose you get the highest proportion of variation for three factors. Like for three factors, you get 70% of variation, which means that when you are doing your analysis, you can reduce the dimension of your data to three. But if you feel like you need to go to four factors to get the 70%, then you can choose four factors. Now, the 70% is used arbitrarily here. It could be something else. I'm considering 70% as high, but it could have been another value. It could have been 80%. But what I'm trying to say is that based on diagonal, you can come up to a decision on how many factors you can retain for your analysis. That is for further analysis, like for a supervised learning approach later on. So that's a little bit about the idea of principal component decomposition, right? As I said to you, you can also now plot the principal components, right? When you have got all these different principal components, you can plot them. And we are going to consider a particular example to illustrate this idea of plotting the principal components. To illustrate this principle, to illustrate the principal component analysis, we are going to have a look at the USRS data, which is available from the ISLR package. And this data consists of four variables and also 50 observations. So what we want to do is we have standardized the data first. Standardizing the data means one of the things is that it's always good that you standardize your data. Okay, why is it good that you standardize your data? Because standardizing the data would make things easier. First of all, it will demean the data, but it also reduce the variance with regards to different variables, x1 up to xp, because these different variables are on different scales. And when they are on different scales, if you don't standardize your data, you will have a big problem, because if, let's suppose, variable x1 has a high variance and is on a large scale, it will drive your analysis basically. All right, so you might have high factor loadings on x2, which may not necessarily be sensible. So this is why you do scaling. Not only do you remove the mean, but you also reduce the variance in such a way that this will not have a high will not drive the analysis basically, okay, by getting a high loading on x2 automatically. So standardization is very important principle. So what we are going to do is that we are going to produce a biplot. A biplot is like a scatter diagram, but what it will do is that it will represent the principal component scores. Remember, the scores are the values that you get by applying these one. So for each, like if you have xi2 for the second principal component, if you want the second principal component scores, what you just need to do is for each value of I, that is the 1 up to n, remember, for each value of I, you are going to have an x1, x2 up to xp, right? So for each of these values x1 up to xp, you are going to apply this transformation. You will get your first set of scores that will not be x1, x2, xp now, but they will be your new z1, z2 up to zp. And this will go on for each row of the data. So you will have a set of component scores. Here we go. So the biplot represent the principal component scores and the loading vectors also, right? It will represent the two things, the component scores and the loading vectors. So let's get to this. Here we have, as I told you, four variables: murder, assault, urban, and rape. Now, normally by principle, you won't get only two principal component. You will have three principal component, four principal component here. But the two others are purposely not represented. Why? Because understand something. The first principal component is meant to represent the maximum amount of variance, and the second one as well. Now, the more you move on, the more the rest would represent a lower proportion of variation in the data. If they represent a lower proportion of the data, they do not give us much information on the data. So this is why they can be neglected somehow. So we can look at the first two, but this first two you have to be careful. For this particular context, looking at the first two looks relevant. But for other contexts, we might have to go for a third component. For other contexts, you might have to go for a fourth component. All right. If you have, let's suppose, 20 possible components, maybe you might have to go to up to four principal components to understand what's going on the data. But for the time being, let's suppose these are the two components that summarizes the data a little bit more, gives us summarizes the variation of the data more. So then we consider these two components. So here you have the different loadings, the different factor loadings that are represented. Remember that this is supposed to be a 4 by 4 matrix, all right? A 4 by 4, but here you are getting only the two first principal component that is being given to you here. So we are neglecting the next two principal components. Now, you can plot these principal components. You can plot these principal components because, as I told you here, you would have these different vectors, all right? You have different vectors that exist in the data. You can plot these different vectors on the data set to have an idea of what is going on. So now, not only can you plot the different vectors, but you can also plot the different scores that has been obtained by applying these factor loadings. So if you have, for example, here for murder, you have this principal component. Um, for sorry, for the first principal component, you have these linear combination. It's like we are saying that Z1 equal to 0.536 of murder plus of rape. So what is happening here? If you have a certain value of murder, a certain value of rape, you just need to replace in the value. You just need to replace in there. You will get a Z score for Z1. Then you need to do the same thing for Z2. Apply the formula for Z2. For just imagine you have a data set here. The first observation is here. You would have your new components Z1, Z2. So what I'm trying to say is that when you apply this linear combination for the first set of values of x1 and x2 for the first observation, you replace it. That is murder. You replace the value of murder for the first observation. You replace the value of assault for the first observation in this linear combination. You get a first value of z1. So this is the first value of z1 that you are going to have here. Then you do the same thing for Z2 using this one combination, and you get a second value here. So the principle is like this. And this is done for the first observation, then you will do it for the second observation, and it goes on like this. So finally, if you look at it properly, you will get a set of coordinates to represent each of these rows in your data. And for us, each of the rows in the data represent a particular state or a particular state in America. So then each of these states can be plotted on the plane like that. Okay. So you have these different coordinates representing the state. And what are these states? As I repeat, they are the component scores, right? They are represented by the component scores that you have here. Now, this is one of the things that is plotted. The second thing that is plotted is not only the component scores, but also the component the vector, all right? The, the, uh, the vector, that is the direction of the vector means the direction of sorry, the not the vector, but the loadings that you want to represent. All right. The loadings here represent the direction. It's a weight that is associated with each of these variables, and it will represent a certain direction within the data. Like, for example, for murder, you will have a certain direction that can be represented. For assault, you have a certain direction, and so on. Let's take the case of murder. Right. If you look at the case of murder, you will have for principal component 1, it is 0.535, and principal component 2, it is negative 0.418. So you look at the scale here. So these scales are used for representing the scores. And these scales here, they are used to represent the vectors, or the loadings, rather. So if you look at this one, the first one, you will see that on the first principal component, the loading is 0.53, and on the second principal component, the variable murder has a loading of negative 0.4418. So if you want to have a look at that, you need to look at 0.53 somewhere here and negative 0.418 somewhere here. So murder is going to be represented at this coordinate here. You can do the same thing for assault. Assault will be located here, rape will be located here, and urban population will be located here. So what is happening here is that you also see where these variables are loaded, which one, so you can see which variables are more correlated among themselves rather. If you look carefully at these different variables, you will see that you have 0.5, 0.58, 0.54. Urban population for PC1 is quite small. The loading on PC1 for urban population is quite small. However, the loading of urban population for PC2 is quite high, but it is relatively smaller for the others. So what does it mean here? It means something very interesting. Just looking at these measures, you can have an idea of what is going on for PC1 and what is going on for PC2. PC1 seems to show that these variables are correlated among themselves, whereas PC2 shows a separate variable. Now, we may wish to understand why is it so. We may also come up to an explanation of what the first principal component may represent. If you look at the correlated variable here, the correlated variable are murder, assault, and rape. If you look at these variables, they represent crimes. So in other words, PC1 is like the component which is referring to crime, right? It's a component that is explaining crime. We can have some explanation for the component, but it's not always the case. But here we can clearly see that PC1 is a component that is representing crime rate. All right. Whereas PC2 is, however, representing the population or an urbanization of a state, right? Because it is separate here. It's not correlated with the other variables. It has a higher loading on its own alone. So in other words, we see that this is a separated variable here. So just by looking at the loadings, which one has the highest loading, you will already have an idea that these variables are correlated. But you can also see it on the graph. For example, you can see that rape, assault, and murder tends to be close to each other on the graph, and urban population tends to be very far from the others. Now, if you look at the three variables here, their vectors are very close to the first principal component. Whereas the urban population, its vector is relatively close to the direction of the second principal component, which means that we can already understand that the second principal component is talking about urbanization, whereas this first principal component is talking about crime rate because these are the one that is having a vector loading that is quite close to this first principal component. These are some other information that we can get out of the interpretation of the biplot. We can see which variables are correlated among each other. But in addition to that, there is something else that we can see. Okay, you will see that variable, the component scores, the principal component scores that are on the left, tends to show a relatively lower crime rate overall. Or the lower it is, the lower the level of urbanization, and the more they are on the left. If you think about these axes, the more they are on the left of these vectors, the more they are on the left, the lower their rape rate, the lower the assault rate, and the lower the murder rate. But the more they are on the right, the higher would be the rape rate, the assault rate, and the murder rate. So for example, we can clearly see that Nevada has a high rape rate. Okay, we see that, for example, Maryland has a very high assault rate. And overall, any region that is found to be on this side will have a more or less high crime rate. And the other thing is that the lower they are here, the lower they are, just imagine these as new scales, new data. The lower they are, the lower the level of urbanization as well, right? Like North Carolina, West Virginia, and so on have a relatively low urbanization, but in addition to having a low urbanization, they also have a large crime rate. So some idea about the interpretation of this biplot. So here, California, for example, shows a relatively high level of urbanization, given it is relatively high on that scale, all right? And all the others that are on the right of that scale, on the positive side, showing a high crime rate overall, all right? And these values that are, these states that are relatively in the center there, that are close to zero, represent low crime rate and also an average level of urbanization. Not a low crime rate, but an average level of crime rate and also an average level of urbanization. All right. So these are some of the interpretation that we can make out of the principal component analysis. So visualization step. Okay. So just a few things that we need to understand about the principal components that we have discussed. One of the things is that, as I told you earlier, we want to scale the variables because you can see clearly an example where the data has been scaled and the data has not been scaled. When we talk about scaling, just remember that we are referring to x minus x bar divided by the standard deviation. So we want to take the value, you demean it, and you divide by the standard deviation. That is what we refer to as scale. Anyway, a scale variable is already a centered variable because the mean itself would be zero, right? So this is what we prefer, not only to center the data, but also to scale it to avoid having this kind of issue here. Because normally you will see that the assault variable, if you go and try to do it, you will see that the variation in assault is very high. Not only the variation in assault is very high, the scale is also different from the other variables. This is why you have a high loading on this side for assault, which is not necessarily a good thing. But when you scale the variable, you will see that assault is here and making things a little bit easier in terms of interpretation. Without this, interpretation of what is going on in this data would be very difficult. Okay, so just bear in mind that scaling is essential to the concept of PCA. Now, one other thing though is that if all of these variables are on the same scale, then maybe scaling you may wish to avoid, you may wish not to do scaling. All right. If all the variables are on the same scale, doing scaling might not be necessary. But scaling is especially important when the variables are on different scales, right? This will avoid such type of issues that we saw here. Okay. So that's one of the things that you need to consider when you're doing principal component analysis. The other thing that you need to understand when you are doing the principal component analysis is the uniqueness of the principal components. When we talk about the uniqueness of the principal component, what do I mean by that? The result that you get in a software, let's suppose you're applying the principal component in R, or you do apply the principal component in a different software, you will get basically the same result. But nevertheless, despite having the same result, you might have a small issue with regards to the sign sometimes. Okay, um, if you look at R itself, there are different functions that can be used to run the principal component analysis. All right, and these two functions, you will see that the results are going to be the same, but up to a sign flip, which means that in one of these functions, if you apply the principal component, you might have a negative z score sometimes, but in another software, in another function, you will have a positive z score. The other thing is that in that function, you might see that some of the factor loadings are, let's suppose, negative, but the same factor loading here for this one is positive. All right. So, but one of the things that you need to understand is that what this does not really cause a problem. Whether you have an issue with regards to the sign, the interpretation in the end will be the same. Because just remember that Z is a function of what? Your loadings and your different variables. So if you have a negative sign here and a negative sign, they will offset themselves into a positive sign, like positive, positive. So this is why I told you that if you have such kinds of issue, one is giving you positive and the other one is giving you negative, it's not a problem as such, because the interpretation will turn out to be the same in the end. All right. So this is why I refer to the case that they are unique. The principal components are unique. So don't be afraid with the negative sign. If in one case you have a negative factor loading and in another case you have a positive factor loading, you also need to check the Z score. You will see that they would bring the same interpretation in the end. Okay, in the end you would have the same interpretation. It doesn't change. So just bear that in mind. Okay, that they are unique, they are the same. The interpretation is going to be the same, just the sign may differ, but this does not cause a problem, because in the end it's going to be the same thing in terms of its interpretation. Uh, so that's one of the thing, and then the other thing that we are interested that when we are applying principal component analysis is we are interested in the proportion of variance explained. And the proportion of variance explained is important in the principal component. Normally, the first few principal components will explain the maximum amount of variance. If you have 100 variables, you might have 100 principal components. All right. But you will see that most of these principal components would be irrelevant. Maybe you would have only the first few principal components, like the first three principal or four principal components will explain like 80% of variation in the data. So if the first three principal components are explaining like 80% of variation in the data, you may decide to say, okay, we are going to disregard all the rest that we have and refer to only these first three. And how are we going to get to this is by determining what is the proportion of variation that is explained by these different components, right? Now, the proportion that is explained by these different components is what I already mentioned in the form of a data matrix here. By looking at the diagonal of this matrix S, you will have an idea about the proportion of variation that is explained. You will have an idea of the variance that is explained rather by each of these components. But if you want to find the proportion of variation that is explained by the different components, first of all, let's try to find the variance, right? Or the total variance that is present in the data. The total variance present in the data is one thing. Then what you need to do is to find the total variance that is explained by each component, all right, of the data. The first component, the second component, and the third component. So just imagine the matrix S, all right, which is a P by P. As I told you, the off diagonal will normally be equal to 0, all right? But then you have the first value that is going to be obtained for the first variable and the second value that is obtained for the second variable. And this continues. So the proportion of variation that is explained here would be basically what? If you look at this concept here, the proportion that variation that is explained here would just be equal to this value divided by the total variance that is explained in the data, right? So this value divided by the total variance that we explain in the data. Value explained by component M equal to 1. M represented the component here. If you have a 3 by 3 matrix, all right, if you have a 3 by 3 matrix, 1, 2, and 3, the off diagonal would be 0, as I told you, the off diagonal would be 0, but you are interested in the variance of these three components, all right? So you are interested in the variance of these three components, 2, 3, 1, 2, and 3. So how do you get the proportion of variation explained by the first? Is just by taking the variance for the first component through that formula if you want. You divide the whole thing by the total variance that is explained by all the components. All right. So that is a principle, all the total variance in the data overall, right? This can also be referred as the total variance here or the total variance for the data as a whole. A So remember that things are relatively easy. Why? Because these representations are very easy, as you see, because of the fact that we have centered the data, right? If we did not center the data, we would not have a neat formulae like this. So we want to see the cumulative proportion of variation, because the cumulative proportion of variation, let's suppose if the first to explain 80% of variation, we might be tempted to say, okay, we'll select only the first two variable and neglect the rest, right? So this is why we need to compute the proportion of variance that is explained in the data, because this is what is going to enable us also to understand how many components we need to retain in the data. Now, one of the things that you need to note is that if you have an n by p data matrix, you will see that very often I told you that you would have p components that you can get. If you have p components, so if you have p variables, you would have p components, all right? That's one of the things that I've been mentioning. Because most of the time, what happens is that the number of data that you have, most of the time, the value n is greater than p, right? The number of records that you have in your data is higher than the number of the variables that you have. This is one of the things that happens most of the time, and this is why I'm referring to the case of p components. So each time. But it might happen that sometimes you might have a data set for which the number of records is less than the number of variables. And if this is the case, then you might wish to say that you would have a n minus 1 principal component. All right. If you had 10, let's suppose if you had 10 records, all right, 10 records, 1 up to 10 records, and you have 20 variables. Then, if this is were to be the case, then you would have 9 principal components that would be obtained from the data. But as I said, this is a very rare case. We rarely get such type of cases, all right? But if this is to be the case, you understand that this is what we are referring to here. Now, but how many principal components you will need to use? As I said to you, let's suppose we are referring to a general case where your n is greater than p. So if n is greater than p, obviously what is going to happen? You would need to have p components, right? Now, if you have, let's suppose 20 variables, this means that you would have 20 components, principal components. But you will see that out of these 20 principal components, Z1, Z2 up to Z20, many of these components would be irrelevant. Irrelevant because the proportion of variation that they explain in the data are very small. So then we may neglect all these, but consider only those components that explain a major part, a higher proportion of variation. And most of the time, these are the first few components, right? It is the first few components that explain the maximum amount of variation. Now, but what do I mean by the first few? There is no real guidelines or real rule that can be applied to decide on that. Although there is some guidelines, yes, but you don't have a rule as such. You can have a guideline, you can get some idea about how many components that can be retained for analysis. What I mean by analysis is, like, for example, for this purpose of interpretation, as I just did in the biplot, or not as necessarily for the purpose of interpretation, but also for applying in a supervised learning method, as I explained to you, to use these to predict a certain variable y. How many would you retain? Now, this is what I'm going to explain. The idea is that the number that you keep should explain a relatively high percentage of variance in the data. Uh, you may decide to take it as 70%, but there is no rule for that. It may be 80% as well. But as long as your number of components that you keep make sense, all right, they are sensible in terms of interpretation. If you decided to have two components and the two components explain the data properly in terms of what's going on, then it's okay. But if you feel that you need to go a little bit more than two variables to explain what's going on in the data, you can go for more than two. There's no real rule about that. But as I said to you, you can have a guideline. One of it is through a script plot. You can do a script plot, all right? You can do a script plot to have an idea about how to decide on the number of data. That's one of the things. What is this script plot? This script plot is going to plot basically the proportion of variation in the data, and you just need to have a look at the elbow to determine that. Okay, let me just give you an idea about it. So it's shown in here. This is a script plot. Okay, you have a script plot here. This is an example of a script plot where you have a proportion of variance explained by each of these components, and based on this script plot you can identify the number of the components that can be used, but we'll get to that afterward. So this is one of the ways of identifying the number of principal components through a script plot, for example. All right. So, or also, as I just said, through when you are starting to identify interesting pattern. Let's suppose if you see that the three variables that you have here, the three variables that you have are the three components are explaining some interesting pattern within the data. So you consider it to be three components, all right? So as I said, there is no rules as such or simple answer to that. It depends on the data that you have and what are the interpretation that you can make out of it. If you go to a fourth component and then you see that there is some loadings on the fourth component, but they do not really have an interpretation, they do not really have a meaning, then you may wish to just focus on the first three. Okay, so normally here we can determine the, as I said to you, you can determine the number of components just by looking at the script plot, or also trying to understand the data that you have. And from the data, if you get interesting pattern arising, you can base yourself on these interesting patterns. So we'll just move on. They are just talking about the same thing that I just said. Uh, Please disregard this slide because it's basically the same thing as the previous slide, all right? It gives you the maximum information there. So it's a little bit similar to the previous slide. You may wish to disregard this, it's just a mistake here. Huh? If you are going to use these principal components, as I told you earlier, in the case of a supervised learning method, that is, you want to use these to predict a certain variable y, then it's relatively straightforward to determine how many components that you need to use. Is just by doing it's just by applying a cross validation, right? It's just to see, you apply it for, let's suppose, two components and see what are the results that you get on the testing set, and then you apply it for three variables now and you see what are the results that you get on the testing set, and so on. So you just need to vary the number and using a cross validation approach or some related approach to determine what are the errors that you get on your testing set if you use two components, if you use three components, and so on, bearing in mind that the more variables, the more components you use, the worse it's going to be on the worse is going to be on the testing set. All right. The If you use too few variables as well, if you use like one, it may not be sufficient. You might have to go for two. So this is one of the things. So, but we can use the script plot as I'm going to show you in the next slide to get an idea about how many factors that can be retained. And normally it's just quite straightforward. It's just by eyeballing through the plot that you will have an idea of how many factors that have to be kept or to be retained. Uh, so Here we go for the script plot. You have the proportion of variance explained. This is why I told you earlier it's important that we get to know what are the proportion of variation explained by the date by each component. Like for the first principal component, the proportion of variance explained for a certain data is 60%, whatever data. And then the second principal component, it's about 25%, and so on. Now, if you look at this script plot, you can see clearly that these values are starting to tail off at some point in time. They are going to tail off and they represent a low proportion of variance in the data. But the first one and the second one seems to explain most of the variation in the data. So if they seem to explain most variation in the data, like 85%, if you look at it, 0.6, I suppose this one is 0.6 and this one is 0.2, but with some addition here. So I suppose about 85% of variation is explained by these first two itself. If 85 is explained by the first two itself, we may decide to say, okay, let's take only the first two, because right now we start getting an elbow right from there. So if this is the case, we just need to say, okay, there are two principal components that can be used in the data, because you will see that start to tail off later on. Okay. Um, the first two is explaining the maximum amount of variation in the data. All right. So here it's relatively straightforward, and you can say, okay, let's take it as two components, because yes, here you see that these two are tailing off or are getting a little bit flat, like you're getting an elbow there. All right. So but the point before the elbow would represent the number of components that you need to select. The points that comes before the elbow would represent the number of components that you need to select. So that is a little bit the idea behind how you may wish to select a principal, the number of principal component. The next step is that we are going to apply this on, we are going to do an activity. Now, just before I move on, just note that the third is explaining less than 10% of variation in the data, and the fourth as well. So, which means that these are not really helpful. So we may disregard them. They do not explain much about the data. So we may wish to disregard them and consider only the first two. So, but as I said to you, it's a relatively ad hoc procedure, right? But there is no well accepted objective way to decide how many principal components are enough. This is one of the things that you need to bear in mind. Okay, though you can have some guidelines, but in the end, you might think that okay, two is not explaining the data sufficiently, so you might have to go for more. So, the next step is that we are going to do an activity where we are going to apply the principal component analysis on the USRS data. Okay, we're going to interpret the output and produce a biplot and obtain a script plot to decide on the number of factors to retain. These are the kind of things that we are going to do now. And as I said to you, this is not discussed in this module, but you have the eigenvalues and eigenvectors that are explained here. How do you find eigenvalues and how do you find eigenvectors? These are explained in these different slides that you can go through on your own. In any case, you've already gone through them in your one modules, so these are disregarded in the explanation here. But bear in mind that in this module particularly, you are not going to be expected to compute these eigenvalues or eigenvectors, but you are expected to interpret what an eigenvalue and an eigenvector represent. Okay, remember that I said to you what eigenvalues represent and what eigenvectors represent. So let's go and do this application here, applying the principal component analysis on the USRS data. We are going to interpret the output, produce a biplot, and obtain a script plot to decide on the number of factors to retain. So we are going to do that in the software R, obviously. We will start by getting the data, but to be able to get the data, we will need to load the library ISLR. And then when this is done, our next step is to have a look at the data. We may just have a brief look at it, just to see what are the variables. And just looking at it, you can clearly see that they are not on the same scales, right? You have a murder, assault, urban, and look at the assault, it's a very different scale. We may also go a little bit further by doing a summary of the US data. So just doing the summary of the US data, you see that the range of values for assault is relatively big compared to the urban for each of these. Now, we may want to do something. We may wish to calculate the variance for each of these variable and have a look at what's going on. If we use the function apply, for the US RS data, by column, all right, by column, we want to calculate the variance for each column, that is for murder, for assault, for urban and rape. We want to calculate the variance for each of these column of the US data, and the variance is defined by the function var. You will see clearly that the variance for assault is extremely high compared to the other variable. This is why earlier, you remember in the slides that I showed you here, this is why I told you earlier that you have to be careful by not scaling the variable. You will have such kind of issue because of assault has a high variation, and also the scale is very different from the other variables. So to avoid such type of things, that's why we'll need scaling. All right, so let's get back to this. We can now perform our principal component. Now, to perform the principal component, there are different functions that are available. All right, there are different functions in R that can be used to perform principal component analysis. One of it is the one that I'm going to show you, but there is another function as well, okay, which is another function which is prin comp. That's another one that can be used as well. Remember that both of them are meant to give you the same results, maybe to a sign flip. All right, we can check it out afterward if you want. So, but let's try this one. So we are going to apply a principal component analysis on, let's call it PCA, on the US data. Now, the US data consists of four variables here. So we are going to run it on the four variables directly. So we are going to use another function which is prcomp, okay? And we are going to do it on the old data set. So that's why I'm going to put USRS, but sometimes you will have to choose which variable you want to do it in the data set, okay? Yeah, the other thing is that, as I said to you, because of this issue of variance that you have here, it is important that you scale the data, okay? And to scale the data, you say scale equal to true. So you can run it down on the USRS. There is no need for you to standardize this variable and then run the principal component. You can just call it here scale is equal to true. So automatically it will rescale the data. Instead of working with the covariance matrix, it will work with the correlation matrix in the end. All right. Instead of working with the covariance matrix, we work with the correlation matrix. So this solves the issue of scaling. So we can just have a look at the result. If you try to remember a little bit about the matrix S that we discussed earlier, the matrix S that we discussed earlier, I told you about the diagonal of the matrix, right? Each of these diagonal of matrix S gave us the variation that is explained by each of these components, the variance that is explained by each of these components, the variance of each component, basically. Now, here it is. These are not the variance, but the standard deviation of each component. So the squared of these values are meant to give you the variance that you get from the S matrix that I'm going to show you afterward. Okay, so but here is something else. Look at these now. You see, you will have here different information. These are the loadings that you have on each principal component. So you have PC1, which is Z1, if you want, is equal to negative 0.535 of murder minus 0.583 of assault, and it goes on like that. Now, when we looked at the example that was given in the slide, it was different. It was positive everywhere. These two were negative, and this one was positive. These two were positive. So, as I said to you, the negative sign does not create an issue as well as such. All right, it doesn't create an issue because it will offset with the value of Z that we have later on. So, like if you are interpreting that um, if murder is increasing, if murder is increasing, what is happening is that in the end, with the other Z score as well, murder will still be, uh, that is, the principal component will also be increasing there, right? Because the negative sign will offset because the Z score that you will get there would be negative, all right? For us, the Z score that we will have would be negative. So the interpretation that you would make out of it would be that if one is increasing, the other is still increasing. The other means the PC1. The component scores is also increasing. It won't change. So the sign does not really create an issue here. Just bear that in mind. So but for this one is different. Like if one is increasing, if murder is increasing, what is happening? The Z score will be negative on the other side. So if it is going to be negative there, it will decrease. So it's the same as if you would have done it for the case of the slide, where the slide is showing a negative value, but the Z score on the slide would have been positive. So the interpretation is the same in the end. So the sign, as I said to you, is not an issue, but the result should be the same. Maybe we can check the magnitude rather than looking at the sign. Let's have a look at the magnitude of these data. So let me just get this already here. So we can have a look at what's going on. And you will see that for the first two principal components, as I said, you will have more than two, but if you are interested in the first two, these two would be negative, these one would be positive here. So remember that for us, the Z score would be also, if the Z score was positive here, the Z score for this function here, for this application would be negative. So which means that they are going to be offset in each other, resulting in the same interpretation. So this is part of it done. So we move on to the next step is to find a summary of these principal component, all right? The summary of this principal component. Here we are. The summary of the PCA gives us some indication of the proportion of variance that is explained by each of these components. And the proportion of variance that is explained by each component can be found here. This is what I explained here. All right, this is what I explained here, the proportion of variation that can be obtained. But just bear in mind that we don't have the divide by n here, all right? So this one is giving you the divide by n, but the other one is not giving you the divide by n. But in any context, it's a proportion, so it's not an issue. So let's get back here. So we have the proportion of variance that is explained by the first principal component. And let's have a look at the standard deviation. You see, you have 1.5748, and the proportion of variance that is explained by it. Now, if we try to convert that into variance and see what is the proportion of variation that is explained by all of these, let's try to have a look at the different information that are available from the PCA. You have the SDEV, which means the standard deviation. So we want to square this standard deviation and check if it really gives us like the variation. Rather than talking about standard deviation, we'll talk about the variance. If the variance by the first component is really explaining 60% of the overall variance here, we can just check it out. If we type SDEV, we'll get, sorry, if we type PCA $SDEV, we will get all these different information. So what we want to do is that instead of working with the standard deviation, we want to work with the variance. And then by working with the variance, we are interested in looking at the proportion of variation for the first one. The first one means it's giving you 1.5748. Here we go. But I'm interested in the variance. Divide by the sum of all the variance that you have in the data, right? All the variation that you have in the data. So to do that, we do sum of PCA dollar SDEV to the squared. That is, we are squaring. We are supposed to have 62% of the variation here. That is explained by doing that. We can just check it out. Remember that we are doing it with the variance. So here we go. We have a 62% of variation that is explained. And we can do the same thing for the second one. For the second one, we just need to change that to 2. That is, we are interested in this one, 0.998994. It is 0.994. And we'll see that it explains 24% of variation and goes on. So you can also look at the cumulative proportion. I think the cumulative proportion is straightforward to understand. Just take this one plus this one, you get 0.86 and it goes on like that. So here we go. We've got the proportion of variation that is explained by the data, and you see clearly that for us, two component is sufficient to explain 86% of variation. So we don't need to go to the next few ones and just disregard the others. We can produce a biplot now. Just draw the biplot of the PCA that we've computed, and we will see that we are supposed to get the same kind of idea. But the only thing that is going to happen here, because you see clearly that these are negative and this one is positive, when in the slides this one was positive and this one was negative, which means that the direction will change on the inverse side, all right, of the direction will change, and the component scores as well is supposed to change. So let's have a look at the biplot of a PCA. So this is what we get here. The biplot of a PCA is obtained as you see here. By the way, you may wish to rescale these observations if you want. For us, there is no need to rescale these observations. By default, there is a certain scale that is used, which is 1. But if you want to rescale them, you can just get it a little bit smaller. For example, scale equal to 0. Just remember how it looks like before I just run it down. Maybe I just style vertically. So just remember how it looked like firstly, and then if I put scale is equal to 0, we'll see the difference. So it just rescaled the data. Okay, so it depends. Both of it works fine. So here we go. You see, in our previous example, we had the data was on the other side. All right, it was located on the other side, but now it's located on the reverse side as well. But it doesn't matter at all. The interpretation is what matters. So the interpretation will be the same as you had for the previous case. Okay. To have a better idea of what's going on, maybe we could just add the axis, that is the principal components axis, uh, by doing a line v equal to 0. You plot a vertical line at 0 and you plot a horizontal line at 0. So h is equal to 0. So this is what it does to make a little bit the interpretation a little bit easier for us. So this is what we get in the end. So you see that urban population, the urbanization is more alongside the second principal component, right, which is the vertical. PC2 is vertical and PC1 is horizontal. So vertical relates more to the urbanization and the same interpretation that we did earlier, but here it's on the reverse side. Okay. But if you really don't want to look at it in this side, which is a little bit hard to interpret, maybe you might just do some amendment to this graph and reproduce the graph, by the way. If you really want to reproduce the graph, there is a simple way of doing it. Is first of all, you would understand that this matrix is a rotation, all right, which refers to basically the loadings, the factor loadings. And for us, these factor loadings are negative and we want to make it positive, just to change the sign so that we can see the same thing that we saw earlier in the slides to make things a little bit easier in terms of interpretation. So if we want to do so, we know that, as I said to you, when you type the name, you know that there are different objects here that are rotation, sdev, and so on. So we can call for rotation, but we are going to change the sign. That's one of the things that we want to do. But in addition to that, we also need not only to change the sign, but we also need to change the component scores. Now, these component scores are going to be obtained by the x, by the way. If you do PCA $x, you will see that you can see the component scores that have been obtained for each principal component. Let me just try something. View x. Here we go. You will have now, instead of having variable one, murder, etc., etc., you have the four principal components, and these are the new values, the transformed values, the Z1, Z2, and so on. All right, these are the new values which have been transformed. You don't have the original data now, that is, you don't have view. You don't have this now, murder, assault, urban, and so on, but you have a new set of latent variables, all right, as I just showed you. So the X are representing the principal component scores. Just bear that in mind, these different information that you have in this uh, output. You have the loadings that are here, the factor loadings, which are the eigenvectors of your scaled uh, covariance matrix. And then you have the eigenvalues in terms of variance. The square of these represent the eigenvalues, right? The square of these values represent the eigenvalues. You have the eigenvectors. For each of these, you have the for each eigenvalue, you have the eigenvector. And also the component scores can be obtained through $x. So what we want to do is we want to change these different outputs that are given by R. So we have PCA dollar rotation, which is a factor loading, is just obtained, is just going to be equal to, we are going to change it to minus PCA dollar rotation. We just change the sign here, eh? And we do the same thing. PCA dollar x is equal to the minus PCA dollar x. We are just changing everything, and then we plot the biplot again, and the biplot will use PCA, so we are just replacing it in the PCA as itself. All right, so we just plot biplot PCA, and let's have a look. It will just interchange everything. So here we go. We can just plot our upline v equal to 0, h equal to 0, and we get a better interpretation interpretation of a result. As you saw here, it's the same thing that we got in the slide. I'm going to skip the interpretation, which will be given that we already did it. Okay, that's a little bit how you can get the um, by you can get the biplot. The next step is that we can also plot the script plot to get an idea of what's going on. But to be able to do the script plot, we will need to find the variance. All right, first of all, let's suppose PCA variance, we call it PCA var, okay, and this is obtained by doing PCA $sdave, as you saw, to the squared. We get the PCA variance. And then what we are going to do is that we are going to plot these information. This is what is going to make our script plot. But what we are interested in, the proportion of variation that I explained earlier. So we'll make it easier. Proportion of variance explained is going to be equal to the PCA variance that we've got divided by the sum of PCA variance. All right, the PCA variance that we've got for each and every one divided by proportion of the sum of the PCA variance. Let's have a look at the PVE. Have a look at what you got. It's the same thing that we got earlier. That is, it's the same thing that we have here. It's the diagonal of the matrix S that I explained to you earlier. So here we go. But I did one by one here, but you got it on one side, only once for all these different components. So that's what I'm doing here. We are squaring these different values. So then when we've got the proportion of variance explained, that has already been obtained, okay, because you would note that the names of PCA does not provide for the proportion of variance. You can get the standard deviation, all right, but here you don't have the proportion of variance as such. But you could have obtained it by calling it S and then trying to find the names of S, and maybe you will get the proportion of variance directly. But in any case, it's quite straightforward. You could have done it there, as I did. Now, the next step is to plot these. All right, we want to plot these PCA. So to plot them, we just call plot PVE. We'll call it PVE, and the label of the x-axis was basically the components. All right, the principal components, the number of principal components, and the label of the y-axis represented the proportion of variance explained. So we can just write it down, x lab equal to principal components, the principal component, and the y lab represent the proportion of variance explained. I just call it PVE here, but you could have written it. And normally the proportion of variance explained would have a y lim of c0 to 1. Okay, 0 to 1, and the type is important so that you can see the character. Otherwise, you might have a bit difficulty. If you just don't do that, you would have a series of points, but if you just do type is equal to L, you would have a line that is smooth and would be hard to interpret. So we want a broken line so that we can differentiate among the different components. All right. So here we go. Otherwise, as I said to you, you would not have seen these circles. So, but maybe we can improve that a little bit by CH is equal to 19. So if we did not do that, we will just have a smooth line and would have been hard to see what is happening here. So this is our script plot. We can call it main script plot. Main equal to script plot. Okay, and we see we have already been interpreting that, so we are just going to disregard the interpretation for the time being. So this is a little bit what we want to do. By the way, I just told you something. We could also do the same thing that we just did here. Instead of calling it comp, we can just do the same thing but using a different function, and let's have a look at what are the results that you get. So before I do that, let's just call PCA again to see the result that we just got using the previous function. I'm going to use PCA1, call it a new function by using pre-comp of USRS. But there is one thing, is that the scaling here is equal to true, implies that when you are using the printcomp function, you don't have a scale equal to true. You don't have this argument scale here. The thing that you need to do is that you need to say that the correlation is equal to true. So instead of working with the covariance matrix, you are going to work with the correlation matrix. That's the only difference by using printcomp. If you want to get the same result, you have to use core is equal to true. All right, it's the same as working with scale is equal to true. All right, so let's have a look at PCA1, and maybe the name might be different in terms of how they call things, but overall they should give you the same results. Here we go, we have the same variance. So the other thing is that we can do summary of PCA to have a look at what is being given. And the summary of PCA1, you have again the standard deviation of each of these variables that are given, the proportion of variance that is explained, and so on. Okay, if you want to get the loadings, let's have a look at the names of a PCA1 function. Oops, here we go, names of PCA1. So you will see that there is loadings here. So they basically the same, just given different names, like you have scores, which is X on the other side, and the loadings. So let's do PCA1 loadings and have a look if we get the same thing, or is it going to be different in terms of sign. So we see that the signs are meant to be different here. Let's just compare it again with PCA rotation, and let's have a look. Here we go. You will see that they are this PCA dollar rotation, but now be careful because I have changed it earlier. You see, I've done the changes here. This is why you're getting the same thing, because I've done the changes here. This is why you're getting the same thing. Okay, if I did not change this, if I didn't change that, you would see that they would have been negative everywhere here. This would have been positive, this would have been negative. So, but overall, you see that the results are the same. Now, there is one thing that I want to do in addition to that, is that you remember that I told you that the sum of one of the constraint that we did on these analyzers was that the sum of the squared loadings should be equal to 1. Each time we did this constraint, the sum of squared loadings should be equal to 1. Is it really the case that the sum of squared loading is equal to 1? Maybe we can just have a look at that and give it a try. Here we go. Is it the sum of the squared loadings? Are they really equal to 1? So let's give it a try and check it out. We can do that by just checking the sum. So in other words, we are trying to square these loadings. Remember that this is Z1 is equal to 0.535 times X1 murder plus 0.583 times assault plus this next loading times urban plus this one times rape. So what we said earlier is that the squares of these loadings should be equal to 1. So let's give it a try to see if this is the case. So PCA, the rotation to the squared, and you don't do the sum of them. And oops, excuse me here. Yes, sorry. What I did here is I did for the whole matrix, but I need to do it for this column, right? For this one first. So PC1, here we go. I just missed this index here. That is, I'm looking at the column. Each column has to be done separately. So for this column, it should be equal to 1. The sum of PCA rotation for this column should be equal to 1. To the square, sorry, should be equal to 1. So let's have a look. It is equal to 1. If you do the same thing for the second principal component, you should see that it is equal to 1 again. And again, these are the constraints that has been set earlier. So these are the information that you got, constraint that has been set earlier. So that's a little bit all that we want to have a look at in terms of the application of a PCA in R. For the interpretation, we've already been going through them earlier. So I think you have all the necessary information that we have on PCA. Remember that the interpretation that you make out of the components and how many components you decide is relies solely on your interpretation of things and how your data is. It is data specific, in other words. Okay, it's data specific. There is no rule for that. Uh, so that is all for PCA. So see you in class. Take care. Bye bye.